Hello everyone. In this next section we're going to be looking at a couple of the uses for residual plots when we're performing a least squares regression. So there's two things we're going to look at. We're going to look at when that violation of that condition of linearity is made and what it looks like in the residual plot. And then we're also going to look at instances of what we call subsets in the data where perhaps there might be more going on in the relationship than we originally believed. So the first thing that we have to remember is that linear regression is only going to work for data that appear to fit this straight enough condition. So linear regression is only for linear relationships. If the relationship is curved, then we're going to have to use some different steps, and we're actually going to see that in the next chapter. Our goal when we're looking at the residual plot is that we don't see any pattern at all. We want kind of this nebulous cloud of points in the middle of the plot. We do not want to see any sort of patterns. So here's a few examples of some residual plots. The residual plot that we're most interested in is the first one, letter A. And in this case, we don't see any sort of systematic under or over predictions. We see constant variance in the predictions across x values. And that's kind of our goal. That's that idea that we want to see nothing in a residual plot. Every other example on the screen, B through F, are all examples of things that we do not want to see. If you see something in a residual plot, you're going to probably most likely to see something that looks like letter C or maybe letter D. So in letter C, we see that biased appearance where there's systematic under and over predictions, but you do have fairly constant variance across the predictor values. But in D, you do not have a pattern, so the data is probably linear, but then you start seeing that these prediction errors continue to grow as we move across x values. So in both of those cases, we're going to learn about some procedures that will help address those problems, but for right now, we are looking for the residual plot that you see in letter A. If asked whether or not a linear model is appropriate, letter A is what you're looking for. So here's an example. We have dive heart rate versus duration, and then in green we have residuals versus duration. So when we look at the scatter plot with the red data points, it may seem that the straight enough condition has been met. The data appear to be fairly linear. But actually, when we look at the residual plot, some of the problems in the original data are almost magnified. So what we begin to see is that there is a little bit of a curvature, and we still have this issue where the prediction error actually is quite large at the beginning, but then actually shrinks as we move across our x values. So if we look back at our previous slide, we actually see something that looks like graph F, only perhaps flipped around a little bit. So not only do you have these systematic under and over predictions, but you also lack that constant variance in y. So whenever we perform any regression, we're going to want to make sure that we always graph the residual plot. And remember, for the AP exam and any other test we take in class, it is really important for you to graph both the scatter plot and the residual plot, in particular if you're going to end up referring to them. So if you say that the residual plot showed that the data were linear, we need to see what that residual plot looks like. So some of the other subtleties that the residual plot might start to show is that the data could be grouped in interesting ways. And this doesn't always happen, but it is something that we are going to want to look for. So in this particular case, we're looking at a histogram of the residuals and a scatter plot of the residual from the calorie and sugar data in cereals that actually comes from our textbook. So if we look at the histogram of the residuals on the left-hand side here, what we start to see is that we almost have this perhaps bimodal data set. So we notice that there's a couple of peaks in the middle, and then there's some unusually low residuals to the left and some unusually high residuals to the right. And if we color code those observations on the residual plot on the right hand side here, what we start to see is you have these green X's at the top that have unusually high residuals. You have these red squares at the bottom that have unusually low residuals, and then you have the majority of the observations through the middle. If we were to ignore the green points and the red points, you would have a pretty nice looking residual plot, a residual plot that we wouldn't worry about too much. So by examining the residuals in this case, we may have discovered some groups that are different from the rest of the observations in the data set. And what's really important is if there are groups, we're going to want to consider carefully how we're going to analyze the data. That is, do we want to look at the data as one whole group, or do we want to separate the data into separate subsets, which may allow us to add to our analysis? So one important thing about regression modeling that's usually not mentioned is that all of the data should come from the same group. So what we wouldn't want to do is we wouldn't want to start mixing data, because then if you need to make a prediction, you're going to probably end up with some interesting results because you've really combined two groups of data to make that regression equation. So when we decide that there are groups in a regression, what we're going to want to do is decide, well, what's going to be the most beneficial way for us to analyze this? Are we going to want to model them separately, so that is, create a different regression line for each group, or is it appropriate to model them all together? And really the context of the problem is what's going to lead us to figuring that out. So in the case of our cereal and our calories in our supermarket cereal, if we separate these by groups, we start to see a really interesting pattern. If you notice, the red regression line and the blue regression line are from the first and second shelf at the supermarket. If you remember from your Algebra 1, the slopes of both of these lines should be pretty low. In fact, they're going to quickly approach 0. What that suggests is that as sugar increases, calories do not increase by much, and that relationship isn't particularly interesting to us. On the other hand, if we look at the data points that represent the third shelf, what we start to see is that line has a fairly substantial positive slope. That is, as sugars increase, the calories increase. In this case, what makes most sense for us is to model each of these sets of data separately. And the reason we would want to do that is it's easy to predict the calorie content for the cereals on the first and second shelf because the calorie count doesn't change much. However, a model created just from the third shelf cereal should give us better predictions to predict calories for that cereal.